there. So this is day 1 of thermochemistry. Today we're going to talk about the law of conservation of energy and heat transfer. A lot of stuff that you already know, so that's a good thing. And we'll talk about whether or not a reaction is exothermic or endothermic and what those two things mean. So thermochemistry is the study of heat changes that occur during a chemical reaction. There will be either heat given off or heat absorbed during chemical reactions. The universe is made up of matter and energy. According to a recent publication by the BBC, which I did not know this, only about 30% of the universe is matter, which makes you think, what is the rest of it? There's a lot of energy in the universe. So matter is anything that has mass and takes up space. That's a very elementary definition. That's the one that you've had since you were little. Matter is anything that has mass and takes up space. So if you look around your room, what are 3 examples of things that in the room that would not be classified as matter? Remember, it has to have mass and take up space. A lot of kids will tell me air, and that is not true because air is made up of gases, and if you look on your periodic table, gases have a mass. So what 3 things may not be classified as matter? Well, light for one thing, sound, and heat. Things that are not matter, really any waves are not considered matter. Those are the electromagnetic spectrum waves that come from the sun. Remember that we've talked about those already, radio waves, microwaves, infrared light, visible light, UV light, X-rays, gamma rays, those are all energy. In red down here at the bottom, air is matter. Remember, that may be a test question. Air is matter. It's made up of gas molecules and they actually have a mass. So the law of conservation of energy is that energy is not created nor is it ever destroyed. Instead, energy moves between materials, but it can also change form. Like if you put batteries into a flashlight, that chemical energy within a battery doesn't go away. It's not destroyed. It gets changed into different kind of energy like heat and light that the flashlight gives off. In a chemical reaction, all the energy is accounted for as work, like actually doing work, stored up energy, or as heat. A lot of energy is given off as heat. Energy has a lot of forms, a couple that you may be familiar with from 8th grade. Kinetic energy and potential energy. Kinetic energy is the energy of motion, and potential energy is energy at rest or stored up energy. Chemical potential energy is energy that's stored within chemical bonds. When those bonds break, there's energy given off, or the energy is absorbed in order to break those bonds. But inside of a chemical bond, there is energy. Thermal energy is energy that comes from heat. The heat is generated by the movement of particles within an object. Now, everything is in motion. We just don't always see it. Gases have a lot of motion to them. They're in constant random motion. But that's what thermal energy is energy that comes from heat. This cartoon suggests that eggs can be cooked on the sidewalk. Look what Maxine says. This heat wave is brutal. Not only is it hot enough to fry an egg on the sidewalk, but you can use your mailbox as a toaster oven. So the energy, it moves from the sidewalk to the eggs to cook those eggs because the sidewalk is what's hot. Heat always moves from hot to cold. I tell my students, you stand in front of the refrigerator long enough, Mom will say, shut the refrigerator, you're letting all the cold air out. Well, actually what's happening is you're letting the warm air in and it's displacing that cold air. But don't tell Mom that. Just nod your head and say, yes ma'am, I'll shut the door. So, but energy, heat moves from things that are hot to areas that are cold. Thermal equilibrium is heat transfer that will continue until both objects are the same temperature. Hopefully, the polar bear doesn't look like that's going to be happening. That's not going to be good. See this example here of the iced tea. You put the ice in the tea, and eventually the heat from the drink melts the ice. Heat moves from, remember, it moves from hot to cold. So it moves from the warm tea to the cold ice until the ice and the tea are the same temperature. Same thing here. You put your hands around your warm coffee mug. The heat is going to move from the warm coffee mug to your hand until everything is the same temperature. Insulators are something that slows down heat transfer. Nonmetals And materials with air pockets are really good insulators. Like up here, you can see the insulation that's being put into your home. In winter, it keeps heat from leaving your house, but in the summer, it keeps heat from coming into your house. So remember, heat energy moves from hot to cold. So in the wintertime, you're trying to keep that warm air in. You're trying to keep it from moving outdoors. And in the summertime, you're trying to keep that outdoor heat from moving into your home. Conductors allow heat to transfer. Metals make really good conductors. Here is a metal pan is a very good conductor of heat. It's cooking those pancakes. So the heat is moving from the burner to the pan, and then from the pan to the pancakes. Solids transfer heat better than liquids or gases. Gases make good insulators. That's why windows are argon filled. That means that in between two very tiny panes of glass in your windows, there's a gas like argon, and it keeps the heat from being transferred through your window. Okay, it acts as an insulator there to keep the heat out in the summertime and keep the heat in the wintertime. Thermal energy is transferred in 3 ways, and I bet you've heard of all 3 of these: conduction, convection, and radiation. Okay, this is the 3 ways that thermal energy is transferred. So conduction is what we start with. Conduction transfers heat through particle collisions. This is an actual touching. Conduction requires a touch in order to transfer the heat. Heat transfer through conduction is heat transfer through a solid. The speedy molecules in the heating coil bump into the pan down here. The fast pan molecules then bump into the bacon, heating up the bacon. So it moves from the burner to the pan to the bacon. That is heat transfer through conduction. It requires touch for transfer. It's definitely not effective in a gas, because gases are kind of hard to touch. It primarily occurs in solid. Here we have turtles sitting on the rock. The turtles are being warmed because that rock is hot. So they sit on that rock, and the thermal energy transfers through conduction from the warm rock to the turtle, which is a little cold. Convection is another way that energy is transferred. It transfers heat through currents in a liquid or gas. Whatever it is that's transferring energy in convection has to flow like a liquid or a gas flows. Hot liquids and gases are less dense, and then they'll rise. Okay, they'll rise to the top. Like up here, the hot air rises to the top where the ceiling is. And it causes convection current. So these currents transfer heat through the liquid or the gas in that way. If there's no current, how do you know that something's convection or not convection? If there is no current, there is no convection. Okay, that's one way to think of it. Convection current can only happen in gases such as air, or in liquid such as ocean water or lava. Not solid particles, because solid particles can't move, they can't circulate, they can't flow. So here you have convection currents inside boiling water. The water's heated and it moves up through, because it's less dense, it moves up to the top of the water where it's cooled, and then it sinks back down again. Same thing is occurring here inside the earth. So the magma, the hot magma, is heated at the core of the earth where it's hot, and it moves up through the mantle where it cools some, and then that convection current occurs. Much of the weather on earth comes from convection currents. The sun warms the air at the surface. Warm air rises, causing winds. When the air cools, it falls back to the ground, forms this nice little current. See? It warms, and then as the water goes out over the water, as the air goes out over the water, warms, and then the return flow comes back to the earth, and it cools, and then it warms. It's just it's a big circle. Okay, it happens different at night than it does the daytime. See, up here is the daytime. It's cool over the water, then the breeze brings the warm air in, is heated by the sun, and it returns over by the water to cool again. So these currents exchange energy through convection. Heat doesn't rise. Warm air carries heat energy as the warmer air rises. So radiation is the last form of energy transfer. Heat transfer through waves from the EM spectrum. Examples of radiation: heat felt from a campfire. Radiation is the only type of heat transfer that it can happen in the vacuum of space. Radiation transfers heat in all directions. Convection currents only rise, so radiation can happen in all directions. Only radiation, though, requires no contact. Both conduction and convection require contact of some sort. Radiation requires no contact. Okay, there's no contact between this poor guy and the sun, but sure enough, he got burned. All energy on Earth comes from the sun. Space is a vacuum. There's no matter. It's a vacuum. So only radiation can travel through space to the Earth. That's the only type of energy that can be transferred through space is radiation. So what do these mean? Conduction is transfer through direct contact. An example would be whatever you can think of, whatever example you want. You know, maybe your hand touching a hot pan. That's an example of conduction. The heat goes from the pan to your hand very quickly. Convection is transfer of energy through currents. You know, maybe you want to show the currents in boiling water. You know, the water boils, and as it heats at the bottom, the hot water rises to the top where it cools slightly and then sinks back down, and it forms a convection current. Radiation is transferred through waves, so you may want to draw that poor guy sunburned and the heat rays coming from the sun. In studying heat changes, think of defining these two parts as the system and the surroundings. So the system is the chemical reaction, and the surroundings is literally everything else. Okay, the system is just the chemical reaction. The surroundings is everything else. So we're going to talk about endothermic and exothermic reactions with regards to the system and with regards to the surroundings. So you need to know what those two things mean. Essentially, all chemical reactions involve either the release of heat when bonds are formed or the absorption of heat when bonds are broken. Endothermic reactions are where energy is absorbed by the reaction from the surroundings. So whatever it is will feel cool to the touch. So in the reaction where you mix baking soda and vinegar, that is an endothermic reaction. If you feel that, if you do that reaction in a little baggie, you can actually feel that it's cold. Okay, it will feel cold to the touch because it's absorbing energy from your hand into that reaction. An exothermic reaction is where energy is released by the reaction, and the reaction will feel warm to the touch. Here are the two reaction pathways here. Here's a reaction where energy is being put into the system. And look, the energy starts out low but ends up high. That means energy has gone into the system. Endothermic energy is into the system. Energy starts high and ends low. I'm sorry, it starts low and ends high. Sorry, I'm pointing, saying the wrong thing. Energy starts low and ends up high. That means energy has been put into the system. An exothermic reaction is one where the energy starts high and ends up low. And look, energy has come out of the system. That's why there is a difference there. That's why it starts high and ends up low. Energy has been released in an exothermic reaction. These are different graphs that you'll see in different either exothermic or endothermic. So we're going to look at each one of these and try to determine whether we think it's exo or endo. So this one, reactants start low but end up high. So what do you think that is? It's an endothermic reaction because they start low and end high. Energy has gone into the system. Here, we start here at 45 kilojoules, but look, we end up lower down here after the reaction has occurred. So what has happened? Well, this much energy has been lost. This is an exothermic reaction. Okay, reactants start low and end up high. That's an endothermic reaction. Energy has been gained. Another endothermic reaction, look, reactants are here and products here. That means energy has gone into the system. This next graph, reactants start here, products down here, which means, look, we've lost this much energy. Okay, from here to here, we've lost this much energy. This is an exothermic reaction. And this last one is another endothermic reaction. Okay, enthalpy. Enthalpy is delta H. That's the symbol for enthalpy. Enthalpy change measures the amount of heat released or absorbed in a reaction. Okay, it is given the symbol delta H, which is red, delta H. Delta H is the final heat minus the initial. Final enthalpy minus the initial. So when you're looking at the graph, you're looking at the graph from the final point to the initial point, and that tells you the enthalpy change. So final minus initial. Okay, so in this endothermic reaction, final minus initial is the delta H here is going to be greater than 0. When it's greater than 0, it's an endothermic reaction. Less than 0, so a negative number, will be an exothermic reaction because you've given away energy. You start high, you end up low. Your energy has gone away. Delta H is going to be less than 0. So in an exothermic reaction, reactions start high, products are low. Okay, heat is released, and your delta H is going to be negative. This is going to be a really good graph for you to memorize. In an endothermic reaction, reactants start low and end up high. We've gained energy. We've absorbed heat. The delta H is positive. Okay, this is a video that's inside a video that you can click and watch. So let's watch this real quick. Well, let's not. I'm afraid to. You can play it on yours and it'll be fine. Let's see. There we go.
Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 39. It's activation energy. Imagine if I try to roll a ball up a hill. If I get enough energy into that system, the ball's going to roll down the other side. In other words, there was a certain amount of energy that ball had at the beginning. We'll call that potential energy, and then we've lost some of that potential energy. But the ball just didn't go there on its own. I had to put a certain amount of energy into it. And in chemistry, we call that activation energy. Now, it's not only balls rolling up a hill and down the other side, it's chemical reactions. You can think of this as the reactants on this side, and this as products on the other side. And so we're only netting this amount of energy between here and here, but there's energy that you have to put into the system. Let's say we have an endergonic reaction like this, one that requires energy. Well, I'm going to put more energy in. I'm going to get some of that back. If we were to look at the energy change, then everything above that is going to be the activation energy. What if I don't have enough activation energy? Well, I can put some energy in, but if I don't have enough, then it's going to go back to where it was before. And so activation energy is how much energy you have to put into a system to have a chemical reaction occur. And it's
okay, so there you go. There's another explanation of activation energy. It's the amount of energy that's required to activate atoms or molecules to a condition where they can undergo a chemical transformation. So exactly what he said, activation energy is the energy required to get a reaction going. A reaction is going to require a certain amount. Some will require more than others. Okay, but activation energy is the amount of energy that's required to activate those reactants in order for a chemical change to occur. Oh, let me go back one. We calculate activation energy. This is really simple, so don't overcomplicate this, kids. Take the highest energy minus the initial. So when you're looking here, that is the highest energy point. Where is the initial? It's down here. Okay, highest point on the graph minus the initial. That's going to give you an activation energy. Okay, so this is my activation energy here. This is my activation energy here. Okay, it just requires different amounts of activation energy. So for calculating enthalpy, let's do a couple of examples. We're looking at this reaction here, right here. So I start here at 45 kilojoules and I end lower. What type of reaction is that? Endothermic or exothermic? What is the delta H? Remember, delta H is final energy minus initial. So 10 minus 45. And how much activation energy is required? So look here, for activation energy, 103 kilojoules minus 45. That is going to give us the activation energy. Okay, negative delta H means it's exothermic. Okay, graph number 2 is a different graph. We start here at 50 kilojoules, and look, we end up here at 100 kilojoules. So it looks like we've gained some energy here, energy into the reaction, which means it's what? Yeah, you know. What about the delta H? Okay, delta H is 100 minus 50. 100 minus 50 is positive. Positive delta H is going to be an endothermic. How much activation energy is required? Well, a whole bunch. 250 minus 50, 200 kilojoules. Okay, number 3 is the graph endo or exo. We start at 40, we end at 20. Looks exo to me. What's the delta H? Final minus initial, so 20 minus 40. And how much activation energy? 100 minus 40 kilojoules. Okay, we're going to stop there, and we will talk about heat curves and phase diagrams next time.